In this session, we'll be understanding the principle of operation of induction motors. A single-phase induction motor and a three-phase induction motors have very similar operating principles. The only difference is that a single-phase induction motor is not self-starting, while a three-phase induction motor is self-starting. The self-starting here actually refers to the production of rotating magnetic field in a three-phase induction motor, while as a single-phase induction motor will not be able to produce a rotating magnetic field of its own. Since the rotating magnetic field cannot be produced inherently in a single-phase induction motor, it is termed as non-self-starting. Any polyphase induction motor, be it having two phases, three phases, four phases, five phases, or so on, will be able to produce a rotating magnetic field of its own and hence will be a self-starting induction machine. In principle, we in theoretically or practically speaking, we mostly use single-phase induction motors and three-phase induction motors. Hence, the focus will be on single-phase induction motors and three-phase induction motors. Uh, Before we move ahead with the principle of operation, we'll understand how an RMF is actually produced in AC machines once again. To understand rotating magnetic field, we need to first of all understand the right hand thumb rule. The right hand thumb rule simply states that if the curl of the fingers point towards the direction of current, if the curl of the fingers point towards the direction of current, the magnetic field will be shown by the thumb that's actually upwards. So in other words, if I say we have a coil which definitely has two ends. On one end, the current is entering this coil shown by crosshair, and on the other end, we'll show a dot that will actually refer to uh, the current coming out of the conductor. So crosshair refers current moving into the conductor, and the dot will actually mean that current is coming out of the conductor. Now, if we apply the right hand thumb rule here, that means the curl of the fingers will indicate that current is flowing into the board and coming out of the board from this direction. In that scenario, we can simply say that the thumb that will be indicating in the direction upwards will point towards the direction of the magnetic field. The right hand thumb rule simply states that if we hold the curl of the fingers as pointing towards the direction of current, the thumb will indicate the direction of magnetic field. In the first scenario, let's say for example we have a single phase induction motor. The single phase induction motor, it has only one winding, one phase, that's with its terminals A dash. An AC current is flowing through the coil terminals AA dash. So that means we will have a positive half of the current and we will have a negative half of the current. Positive half of the current, let us assume, we'll say that positive current means into the board and negative current means out of the board. So during the first half of the uh, waveform, from 0 to pi, the current is positive. That means from terminal A, the current is into the board, while as from A dash, the current is coming out of the board. So by the right hand thumb rule, we can say that we can say that our magnetic field lies in this direction. From 0 to pi, the current will be positive in A and it will be negative in A dash. So the right hand thumb rule will always stand. Only the magnitude of the magnetic field will decrease, but the direction of magnetic field will remain same. So as we move from 0 to pi, we can say that our magnitude of magnetic field increases as we move from 0 to pi by 2, and it decreases from pi by 2 to pi, but the magnitude is decreasing, but the direction of magnetic field remains same. So this is for the positive half cycle of the current. Magnetic field direction is same. Now, if we is now if we take the next half cycle of the AC current, that's from pi to 2 pi, that's the negative half cycle. Here we assume, so from pi to 2 pi now, positive current is flowing from A dash. That means this refers to cross, and a negative current is that means current is coming out of A terminal. That means dot. So by again using the right hand thumb rule, we can see that current is moving in from A dash and coming out from A. That means by the curl of the fingers, we can see the direction of current and the magnetic field will be given in this direction. That means our direction of magnetic field for the negative half cycle will be uh, in this direction. So for the positive half cycle of the current, we saw the direction of magnetic field was like this, and for the negative half cycle, we see the direction of magnetic field is like this. That means in case of a single phase induction motor, although the magnitude of this magnetic field is changing, but the direction of magnetic field remains either in one, it is pulsating, it is either in this direction or it is in this direction. Fine. So, in case of a single phase induction motor, a pulsating magnetic field is produced. It will have only two directions, and a rotating magnetic field is not obtained in a single phase induction motor. Now, let's take a three phase induction motor and see what's happening in case of a three phase induction motor. Now, this is structure of a, three phase induction motor stator. So we have AA dash, we have BB dash, we have CC dash. Now A dash current, say IA dash is the current flowing through the terminals AA dash, that will be given by Im cos omega t or Im sin omega t. IBB dash will be Im sin omega t minus 120 degrees, and ICC dash will be Im sin of omega t minus 240 degrees. So three phase currents are flowing through the terminals AA dash, BB dash, and CC dash, which are naturally placed 120 degrees apart from one another. Let us assume a three phase current as shown in this figure. At omega t equal to 0, we can see if this is current in phase A, this is current in phase B, and let this be current in phase C. We can see at omega t equal to 0, current IAA dash is 0, IBB dash is negative, ICC dash is positive. I'm not concerned with the magnitude of the current, I'm only concerned with the polarity of the currents. So IAA dash is 0, that means there is no magnetic field produced because of the current IAA dash. The current IBB dash is negative. That means if this is B dash, this is A, this is C dash, this is B here, this is A dash, and this is C. IBB dash negative implies, as we have already established before, that a positive current will be denoted by cross and a negative current will be denoted by a dot. Negative current in B terminal will be denoted by a dot, and in B dash the positive current will be denoted by a cross. ICC dash is positive, that means uh, positive current is flowing into C and negative current is coming out of C. Using the right hand thumb rule, we can see that since current is flowing from B dash and coming out of B, the magnetic field produced because of IBB dash will be in this direction. I'm not concerned with the magnitude of this magnetic field right now. Uh, Similarly, ICC dash, the current is coming, the current is flowing from C and coming out of C dash. That means that it will be perpendicular in this fashion. Let me draw this axis here that actually, so these magnetic fields that we have actually drawn here will be perpendicular to this axis, and in this case it will be perpendicular to this axis. So these are the magnetic fields produced as a result of the current flowing in IBB dash and in ICC dash. There will be a net magnetic field. There will be a net magnetic field B net that will be given by the resolution of these two vectors. So this is corresponding to omega t equal to 0. We have a magnetic field in this direction. Now skipping ahead, we'll move to this point. This point on the graph refers to omega t. We'll actually go to this point first. Omega t equal to 60 degrees. At omega t equal to 60 degrees, we see that IAA dash is positive now, IBB dash is still negative, and ICC dash is now 0. So the magnetic field because of the current ICC dash will now be 0. The magnetic field because of IAA dash will look something like this. The magnetic field IAA dash is positive, that means current is flowing from A and coming out of A dash. So if I draw an axis here, the magnetic field now produced because of IAA dash will be in this direction by the right hand thumb rule, and the magnetic field because of IBB dash is still in this direction only. So the net magnetic field, this was at omega t equal to 0. Now the net magnetic field because of IBB dash and IAA dash will be the resolution of these two vectors, that will be in this direction. So this will be B net now, corresponding to omega t equal to 60 degrees. Now at omega t equal to 120 degrees, that's this point on the graph, we can see that IBB dash is now actually 0, IAA dash is positive, IBB dash is 0 and ICC dash is negative. That means IA dash, let me, so now at this point at omega t equal to 120 degrees, IBB dash is 0. That means no current is flowing in the phase B, in the B phase. ICC dash is negative. That means C current is flowing out of C and current is flowing in from C dash, and IA dash is positive. That means uh, at terminal A current is flowing in and at terminal A dash current is flowing out. That means by the right hand rule, the magnetic field by IA dash will be in this direction, and by the right hand thumb rule, the magnetic field because of ICC dash will be perpendicular to this axis in this direction. So the net resolution of this vector and this vector will be along this direction now. So this will be B net at omega t equal to 120 degrees. So we can see the net magnetic field at 0 degrees was in this direction, at 60 degrees it is in this direction, at 120 degrees it is in this direction, at 180 it will be somewhere around here, at 240 it will be somewhere around here, at 300 it will be somewhere around here, 360 that means again at omega t equal to 0 it will be in this direction. So the net magnetic field in case of a three-phase induction motor is rotating in nature. The magnetic field produced because of the combination of the three-phase currents is rotating, and the speed of rotation of this magnetic field is referred to as the synchronous speed. It's given by 120 F by P, where F is the frequency of the supply voltage or the supply current, and that means the frequency of these this current, and P is the number of poles. So for we have actually seen this case for a two-pole structure. For a four-pole structure, there will be a different speed of rotation. So in short, the speed of rotation of the magnetic field, that's called the synchronous speed, is given by the equation 120 F by P, and the units of this is RPM. So if we, so this is the speed of rotation of the magnetic field. A MATLAB simulation of this has been performed, and we can see uh, how a rotating magnetic field is produced by the interaction of three magnetic three vec vectors, three magnetic field vectors produced by three phase currents. Here the black line refers to the magnetic field produced by the phase AA dash. The blue line refers to the magnetic field produced by the phase BB dash. The purple line refers to the magnetic field produced by the phase CC dash. The net magnetic field here is shown by the red line. So we can see as the three-phase currents move from 0 to 360 degrees, how the net magnetic field is produced and how a rotating nature of this magnetic field is obtained. Now we'll move to the principle of operation of induction motors. So we have now understood how a three-phase induction motor will be able to produce uh, rotating magnetic field. Now, the operating principle of induction motor is fairly simple. We simply supply the starter with a three-phase voltage. The starter windings are supplied with a three-phase voltage. A three-phase current will flow through the three-phase windings of the starter. This three-phase current in the starter will produce a magnetic field, and since we have established that this magnetic field will now be rotating in nature, so we can refer to it as a rotating stator magnetic field. The rotating magnetic field uh, comes in contact with the rotor windings or the rotor bars, depending upon the construction of the rotor, whether it's a wound round induction motor or a squirrel cage induction motor. So what we here have is a rotor that's initially stationary, but it's coming in contact. These windings, the windings of the rotor or the conductors of the rotor windings are coming in contact with a rotating magnetic field. So a EMF will be induced in the rotor windings. In the previous session, I already pointed out that the rotor windings are shorted. The shorted nature of the rotor winding means a complete loop is obtained. Since a complete loop is obtained, we can say a current will be established through the rotor circuitry. The current in the rotor windings will produce a magnetic field of their own that will be here referred to as the rotor magnetic field. The rotor magnetic field will be rotating in nature as well, and it will be rotating at the same speed as that of the synchronous speed of the induction motor, that is the same speed with which the stator magnetic field is rotating as well. Now we have two magnetic fields by the principle of the torque induction principle. We already know that torque uh, is obtained as the interaction of two magnetic fields. Here, the two magnetic fields will be the stator magnetic field and the rotor magnetic field. The net stator magnetic field and the net rotor magnetic field. The cross product of these two will give us the induced torque. That means a torque is induced in the rotor. In short, we can simply say because of the interaction of two magnetic fields, a torque will be induced that will cause the rotor to rotate. Now, the only difference here in case of a single phase induction motor is that we will not be able to produce naturally a rotating magnetic field will not be generated in a single phase induction motor. Somehow we have to be able to obtain a rotating magnetic field. Rest of the principle, operating principle is same uh, in a single phase induction motor. It is that means a single phase induction motor operating principle and the operating principle of a three phase induction motor are similar, except for point number two as highlighted here. A rotating magnetic field will not be naturally produced in a single phase induction motor. We have to have some mechanism with which we will be able to obtain a rotating magnetic field in a single phase induction motor. So this is the operating principle of the induction motor. It's fairly simple. The cross product here implies that there'll be a magnetic, there'll be some angle between BS and BR. Let that angle here be delta. If angle delta is zero, that means sine of delta will be zero. That means torque induced will be zero. So in short, we have to produce some alignment between the stator magnetic field and the rotor magnetic field. This was already discussed in the previous session in the constructional details of the induction motor. We discussed that in case of squirrel cage induction motor, we keep the rotor conductors at a certain angle. This actually results in a rotor magnetic field aligned to the stator magnetic field with at an angle. That means delta will not be zero. That means torque induced will not be zero. Secondly, in case of a wound-on induction motor, we discussed that we do not keep the number of stators, number of slots, and the teeth of the stator and the rotor equal, or they are not equal integral wise as well. Uh, that actually results in the magnetic fields never locking with each other. That means the stator magnetic field and the rotor magnetic field will not, the net magnetic field of the stator and the rotor will never be aligned in the same direction. In short, we have to have some arrangement because of which the torque induced in the rotor will not be zero. That means the delta, the angle between the magnetic fields, the stator magnetic fields, and the rotor magnetic fields should not be zero. This all sums up the principle of the operating principle of induction motors. We have so far discussed the construction of induction motors and the operating principle of induction motors. Based upon these two, we'll actually formulate the equivalent circuit of the induction motor in the next session.